Today we're going to start our 11th unit on transformational geometry. This is actually a pretty easy unit and kind of fun. So our first topic is going to be symmetry. I know that your packets came home and they were a little bit disorganized, so I'm showing you all 4 pages of the note packet so that you can pick the right ones for today's lesson. And remember, you can stop the video at any time if you need to catch up on your note taking. So let's first start with line symmetry. So if your object possesses line symmetry, we should be able to draw a line through it so that you get 2 identical halves. So the line of symmetry will occur right in the middle, and the left side and the right side, or the top and the bottom, should be a mirror image of each other. So if you look at the picture of the bridge, and you can ignore the landmarks around it, just the bridge itself, the structure, we can see if I were to draw a line of symmetry right down the center, the left side of the bridge and the right side of the bridge would line up perfectly. They're identical to each other. So that would be a vertical line of symmetry. So the line of symmetry will always divide the object into 2 equal halves. It doesn't have to be vertical though. In this picture, we have land with some trees, and then it's being reflected in the water. So our line of symmetry is actually being drawn right here horizontally, where on the bridge it was vertical. When you deal with line symmetry, it's always based on 2 dimensions. So if you look at the Starbucks logo, and we'll ignore the trademark symbol down at the bottom, but this logo, if we go right down the center, and I'm doing my best here, the left side and the right side of the logo are identical. So you should be able to fold the object along the line of symmetry, and the left side and the right side should match up perfectly. And of all of our previous images, we only had 1 line of symmetry present in the object, but it is possible for multiple lines of symmetry to be present. So in this, we'll assume that it's a square, but we're able to draw a vertical line of symmetry and a horizontal line of symmetry, as well as 2 diagonal lines. So if you fold the object along any of these 4 lines, the objects will line up exactly. With a circle, these are all lines of symmetry drawn, but in reality, you can draw an infinite number of diameters through the circle, and they would all represent a line of symmetry. So the circle has infinite lines of symmetry. This blob, even though it looks like it shouldn't line up, it was set up to have horizontal and vertical lines of symmetry. So I could fold it along either of those and it will line up. This object only has 1 line of symmetry. It's the same on the left and the right. We don't, however, have one horizontally. The top is a little bit thinner than the bottom. So if you were to fold it over that line of symmetry, the top of the X would not line up with the bottom of the X. And this object doesn't have any lines of symmetry. There's no way to fold it so that anything lines up. And all of these objects are, again, 2-dimensional. We could also have what's called plane symmetry. So I can take a 2-dimensional flat plane, and I can make it pass through a solid figure, which is going to be 3-dimensional. When it passes through, we want one half to be identical to the other half. So whether it's diagonal or horizontal or vertical, we have to have 2 identical halves. So in this object, we have a rectangular 3-dimensional object. In purple, we have a plane that is being passed through the object and it's splitting it into two equal halves, kind of in the background here and in the foreground. The blue object is also a plane that is splitting the object, so there's two planes of symmetry, and then this lighter object here going through the center, there's another horizontal plane of symmetry. You can see that this box does look three-dimensional. All of these objects here on the right-hand side are three-dimensional solids, which will be our last unit of study. But depending on the three-dimensional solid, we might have one plane of symmetry, like an object E. This is a cone. It's passing through the top all the way through the bottom so that the front and the back are identical. Other objects like G, a cylinder, they would have two lines of plane symmetry, both horizontal and vertical. So it just depends on the type of object, but plane symmetry is always three-dimensional. We also have point symmetry. Basically, what you want to find is a center of the figure, and it's serving as an anchor point. So here what I have are two line segments that are intersecting at point P. P will serve as my center. There. So what you'll notice with point symmetry is that if you take point A in this diagram, it's going to pass through P, and then it's going to find its new location the same distance away from P. We're calling this location A prime, so that we know that it's the image of A. The same thing is happening with C. C is traveling to point P, which is the center, and then it's traveling the same distance away to C prime to its new location. So although P is the center, it's better classified as a midpoint, and that's a term that we're familiar with throughout proofs. So once you locate any point, we're going to pass through the point, which is our center, and we have one equally spaced on the other side. The same thing is true with this object, even though it's not a straight line. If you look at individual points, so this end here would be the same position on this figure here. If you go through the center, which happens to be the origin, the distance between the points and the origin is equally spaced. So one is the original, maybe this is A, and then this is A prime. We don't know for sure because it wasn't labeled, but all points on this swirly figure would be the same. So on this endpoint here, we would travel our distance to the origin, and then we would travel the same distance away to its new location. So the origin is serving as the center or the midpoint. If you truly have point symmetry, all you have to do is turn the figure upside down and see if it looks exactly the same. So we're going to spin our little swirls. It's going to spin 360 degrees, but you'll see it's the same at 180. There it is. And then again at 360. So if your figure truly has point symmetry, when you rotate it 180 degrees, the image should be unchanged and you should have an identical copy. The same thing is true with our playing card. When I rotate the King of Hearts, he's the same at 180 and then again at 360. Our last type of symmetry is called rotational symmetry. We're also going to find a center or anchor point on the figure itself, and then we should be able to turn it some number of degrees between 0 and 360. So using my star, I'll locate the center. This is where I believe that it is. The point at the top can be turned in this direction so that it lines up now with point number 2, and the star will still look the same. I can keep rotating it in the same direction. This is a counterclockwise, or I'm sorry, it's a clockwise direction. and then point 1 could eventually end up here at point 3. We can keep doing this until it ends back in its home position at the top. When you spin your object, because it has rotational symmetry, it should look the same no matter how many degrees you turn it. So in this case, we are turning it 5 times. So we have a rotation of 72 degrees, and I would have 360 divided by the 5 points on the star, and that would tell me every time I turn this 72 degrees, I'm going to see the exact same shape. The number of times that it takes you to turn it to get it back to its home position is called its order. So for the star, I would have to turn it 5 times to get it back to its home position. So this figure has order 5. My object down below, this is 6-sided, so this is a hexagon. Same thing here. We can turn it in either direction, clockwise or counterclockwise, but because there are 6 vertices, we would divide 360 by 6, and we would know that after every 60 degrees, which is marked here, we would have an identical looking object. Since this has to turn 6 times to get back to its home position, this figure has order 6. If your object doesn't appear to have rotational symmetry, there's a special classification for that, but the last time you rotate it back into its original home position will determine the order. If your object has an order 1 classification, this means that it really doesn't have true rotational symmetry. So a human being might be in order 1. You would have to turn the human being 360 degrees to make sure that the head is back on top of the body and that it looks like a normal human, not that they're upside down. All right, we've worked with both of these objects. We know that they have order 6 for the hexagon, order 5 for the star. We know how many degrees of rotation. This object, while it looks a little bit strange, has identical images as you count. I'm counting all these curly tips, and it appears that there are 8 of them. So we do have rotational symmetry. We can anchor it right here in the center. We can turn it. So we'll do 360 divided by 8 points. And that means every time I turn it 45 degrees, I'm going to get the object to look the same. Since it will take me 8 turns to get all the way back to the beginning, this object has an order of 8. So we've gone through the 4 different types of symmetry. We have line symmetry, plane symmetry, point symmetry, and rotational symmetry. This will be homework number 114. And again, I'm showing you all 4 pages in case you need to reassemble your homework. All right. Please make sure as soon as you finish this that you submit it to me right away so that I can get it recorded in the gradebook. Have a great day.